Today I'll talk about the E. So generally we know there is an equivalence between the between asymptotic symmetries and soft theorems. So here we are going to talk about the same for loop level soft photon theorem. And in this work we are just recasting the loop level soft photon theorem as some asymptotic word identity. But the transformations, like the symmetry underlying this is not yet clear. So this is just the first step in establishing the equivalence. Okay. So these are the contents of my talk. So let's just start. First we'll discuss what are asymptotic conservation laws. This is just some compactification scheme of Minkowski spacetime, and here the massless particles and in future, like as t goes to infinity, they end up here. This is called as chi plus. It's an r cross S2 manifold. So each point here is an S2. So in particular, we'll be interested in the u goes to minus infinity, this sphere of chi plus, which is labeled here as chi plus minus. And similarly, chi minus plus is the v goes to plus infinity limit of this of chi minus. And typically asymptotic conservation laws are stated like this, where this q plus is defined at chi plus minus, and this q minus is defined at chi minus plus, and this is the antipodal matching between the two quantities. So typically the charges look like this. They are some, so these q's are some components of the field strength some component. So I'm not writing the details here, but these are some, and there are some particular fall off. So these are just functions of z bar. So these are particular fall off in u and r. So this just depend on z bar. Now what one can do is just study. Yeah. So this is a particular fall off in u also. So so in general f mu nu will have u to the power n r to the power m. So this will be some particular nm. Okay. So what is done is this particular you take this data at chi minus plus, and then you can just revolve it using Maxwell's equation, and this kind of conservation laws can be proved. So classical electromagnetism, in classical theory, you can actually prove these kind of conservation laws.
U to the power n blows up at plus minus infinity.
Yeah. So here, typically you have u to the power positive powers, but what you can show is that this is of this form, such that n is less than or equal to m. So if you have u to the power this kind of term, then n is less than or equal to m. These are the so you just take Maxwell's equations and try to find the consistent solution. Then this is the kind of solution you get, and this the charges are typically in terms of u to the power 0.
Right. So the independent. That sounds good. So it's a constant.
Yeah.
Well,
these are kind of integration constants.
I'm just wondering about this u to the power n at fixed Rm.
At fixed Rm, yes.
So am I allowed to do that? Am I allowed to work at large but fixed Rn and then expand in u?
No. Yeah, so here
first expand in r.
You first always expand in r.
Okay.
So it's an expansion in u by r. This is still small.
Zero modes will also be on the electric field of the sphere direction.
Yeah. So this is that z bar. It will depend on the rectangular direction.
The part which is related to the soft modes will be electric field of the sphere direction. So
yeah.
It will be UZ.
So you can actually relate this different. So you are saying what happens to FRZ, for example.
I am saying just related to Siddharth's comment that it's u to the 0.
Okay.
Zero mode.
Okay.
Actual zero modes that will appear are not of RU. That will be zero modes of the electric field on the sphere direction. So UZ kind of.
And these are independent?
Yeah, these are not independent. These can be related via Bianchi identities and
There
Maxwell's
is
equations.
an equation of motion,
Yeah.
but there is a way of treating the component that I said as independent that makes it clear, that makes it simpler.
Yeah, so this can be related to FUZ if that's your question.
The simplest kind of work is to work in light cone gauge, like AU is 0.
Okay. But the same data is also in FRU?
In FRU, yeah. So Bianchi identity will, so this will be related to del R, FUZ, del Z, that kind
In
of thing.
particular, FRU will have more than just soft modes. It will also have contributions from soft modes and hard modes.
Yes, true.
Yeah, so FRU had both the contributions.
Yeah, so actually this is the total charge if you see. So later on we will see how to get the soft part of this charge and hard part of this charge. So yeah, so this we will discuss in details later on. Okay?
Thanks.
Okay, fine.
And even this, sorry, just one last, even
Yeah.
the zero mode of this FRU has contributions from hard modes?
No.
No, but once you integrate over U, you're just isolating the
Yeah.
soft mode. Right?
Yeah. Okay. Yeah. So this is the classical statement. At quantum level, one can try to understand the commutator of these charges with the S matrix, and then this S matrix has to satisfy this kind of word identity. And so what is known is that these word identities are equivalent to soft theorems. Okay. This has been understood for many number of cases. In some cases this has not been proved, but it is expected that this kind of statements should be true in general. Now one thing is, in this way of doing it, we have not made direct reference to asymptotic symmetries. We are just constructing some charges that when inserted in S matrix, they reproduce the soft theorems, and those can be shown to be exactly equivalent to the soft theorems. But do these charges come from what kind of symmetries generate these charges? That is not clear.
Why are they not the large gauge transformations on the sphere in some sense? So if I work in AU equal to 0 gauge, then these will be charges corresponding to the gauge transformations.
Yeah. So
which do not die off on the sphere.
yeah. So you start with this charge, understand its action on the free data of your theory,
Yes.
and then you can show that it actually leads to the large gauge transformations for leading soft theorem. But for but these kind of statements are not understood for subleading soft theorem. There, if you try to force it to be a gauge transformation, then it produces a divergent piece in the gauge transformation, which is not yet understood properly, because what happens, you start with some fall off, and then the gauge transformation that you are looking at, that violates the fall off.
This is true.
Yeah. So these statements have to be this way of doing it is doesn't have this problem, because you are just constructing the charges and then inserting in the S matrix, but you don't understand what the transformation corresponding to it is. Okay. So let's discuss soft theorems in little bit of details. So as we know, like a single soft theorem, you start with the n+1 amplitude. We will be considering soft photon theorem. So the n+1th particle is the photon, and we study this amplitude in the energy of the in the limit when energy of photon is taken to 0, and the leading order term is 1/omega. Okay. So this term has been known for a long time, and it's also known that this is an exact quantum statement. And so at loop level, this calculation was done very recently, and so this was and what they found is that there is a log omega term, and this term is absent at tree level. If we study tree level amplitudes, low energy limit, then it doesn't have a log omega term. Okay, and this was explicit. Okay. So just to get an idea, S0 has this form, and as we see, it depends only on the quantum numbers of the interacting hard particles. So in that sense, it's universal. It doesn't depend on any aspect of the theory, and it also depends on the direction of the photon. So this polarization, this is polarization of the photon. It is also fixed by the direction. So these are the only things that the soft factors can depend on. Okay, and now this S log was derived by Bishwajit Sahoo and Ashok Sen recently, and what they showed is that this S log also has a universal structure that is also independent of the theory.
This statement is true to all loop orders that.
Yeah, they have
It's
claimed
one
that
loop
it is
exact or something.
one loop exact. They have claimed that. Okay. So now the thing is to understand if if this term can also be understood as word identity of some charge.
So S log depends on the matter content of the theory.
It depends only on the universal properties of the matter, like its charge, momenta, only that much.
But let's say we're scattering particles of one particular charge. S log gets contributions from loops only of that particle or all charge particles?
All charge particles. So it will treat all the charge particles same, and it doesn't depend on the internal spin also. So fermions and scalars will, if they have equal charges, they will show they will contribute in the same way.
So unlike the leading soft gravity theorem only probes the charge of the particles you are scattering, whereas here this knows about the charge of all the particles that exist in the theory,
Yes.
whether or not you're scattering.
Yes.
Therefore, it depends on the theory.
In some sense, but weakly, just in the particle content. Depends
Yeah.
on mass and charge,
Yeah, mass, momenta, mass and charge.
mass of the particles, the charge particles.
Yeah.
Okay.
Yeah. Yeah. So Campiglia and Laddha, they proposed a new conservation law. This conservation law is now parameterized by a vector on S2.
Sorry, this was for vectors. Is there a statement like this for gravitons as well?
Yeah. So they have derived it for gravity and for QED, photon. There also it is universal. So here I am only talking about photon. That's why I didn't mention. Yeah, and what they showed is that the word identity corresponding to this charge, it is exactly equivalent to the Sahoo Sen soft photon theorem, and they did this calculation for massive scalar QED. Okay, and so our goal is to construct this charge for massless scalar QED and coupled to gravity. Now what we will see is that in presence of gravity, the log omega term gets some corrections, even for soft photon theorem. So we will see what are those corrections, and then we will see that this the word identity corresponding to this charge, that is equivalent to the Sahoo Sen soft photon theorem. Okay.
Maybe you'll tell us this, but roughly from the Feynman diagram point of view, can you tell us what kind of diagrams lead to this log omega term?
Yes. Yeah, so if you have this kind of, let's say you have some scalars, and this I will discuss in details later also. So, and you have some graviton emission, and what we will see is that actually the long range interaction between these two scalars, for example, that will contribute to this log omega term, log omega behavior in this emitted soft photon, and that can come from this kind of terms. Okay, so yeah, this is the Sahoo Sen soft photon theorem, and
If I just look at retarded propagator in presence of the scalar particle, let's say, in this background, at late times it will already have that log behavior, log t or something at large t.
Yes.
Sorry, so from this diagram it does not look like it depends on the details of it looks like it depends only on the charge and mass of the scattering particles once again. Doesn't look like it probes the charge content of the theory, or does it? Suppose you're scattering, suppose the theory is two kinds of particles. You're electrons and scalars. You're scattering only the electrons. The answer for this thing will be independent of whether the theory has scalars or not. Is that right?
Yeah.
Okay. Yeah. So I said it wrong.
Yeah, it will just so if like you are saying, if these two are just electrons,
Yes.
and there are some other scalars in the theory,
It doesn't care.
yeah, this thing doesn't care about that.
Yeah.
But this scalar, but there will be some so this might be.
Yeah, if there's a scalar, it will care about that.
Yeah, then it will.
But it's not like it probes. There's no virtual loops of the charge particles.
Yeah, yeah. In the loops have gravitons or sorry, photons.
Formed by the actual external particles.
Yes, yes.
And if they come inside the virtual loops, you said they are not long-lived or something?
Yeah, basically what this is doing, as she said and as you said, is retarding one on-shell particle retarding the motion of the other. So basically it's the on-shell particles affecting each other. The fact that there might actually have been off-shell other things is not this effect.
But there might be other diagrams.
There might be other diagrams, presumably they don't contribute to this log omega.
This is the question, do they contribute or not? Say, this process can also happen inside the, let's say, scalar loops inside.
Yes, it can happen inside scalar loops.
And then low momentum modes might see this.
Well, presumably this is coming from the part of this diagram where this photon goes off to it.
That photon?
No, that anyway, but even this guy. It's the asymptotic behavior of this guy being retarded by the presence of the other.
Yes, the late time behavior.
And that asymptotic behavior doesn't happen in virtual processes.
Yes, because they do not leave that long.
They don't. Yes.
So this is then quite good, and you not.
It's as good as the first thing. Yeah.
Okay, so this operator just picks out the log omega mode in the n+1 amplitude, and this is an exact statement now, and this is the S log coefficient. It just depends on charges, momenta, this kind of things, and what we see is these two terms look similar, and these two terms look similar in the sense this is the S0 factor. Okay, and later on we'll see that these two terms have similar origins, and these two terms have similar origins.
By the way, this is probably very highly dimension dependent or not?
Yeah, in higher dimensions log omega term doesn't exist.
That's
So this only
It's
is 4 dimensions. Okay.
Just because Green's functions die off too fast.
Right.
Yeah. Okay, so the log omega term is a direct effect of the long range forces. Long range forces in so these are 1 over r kind of fall off.
But wait a minute, even in higher dimensions, is it ever going to, in higher dimensions from loops you don't have any divergences, but you have some derivatives, right? That might lead to new higher divergences in the derivatives which are not present in the amplitude.
Which derivatives?
So in dimensions larger than 4,
Hmm.
there are no higher divergences coming from loops in the scattering amplitude.
Hmm.
But if you take derivatives of the loops, because that will increase higher and higher powers in the denominator in some sense.
Hmm.
So in the derivatives of the amplitude, there might be higher divergences in higher dimensions. So since we had a derivative in the earlier slide, so even in higher dimension, if there is anything to do with loops, if it has to do with loops, it will get affected. But you said it does not have to do with loops.
Well,
Yeah,
it's
there
not-
is-
There is a
yeah.
loop here, but it's a simple.
It's a loop entirely in terms of external.
Yeah.
External object.
Yeah, actually this factor doesn't have any derivatives. It's a multiplicative factor.
You had derivatives of scattering amplitude or not in the last slide?
No. So actually, yeah, this derivative just acts on here. It doesn't act on the
In the
amplitude.
first line, what is this going to be? Double derivative with respect to omega, right?
Oh, okay.
It's
So
just
this
calculating the coefficient of
of log omega, just like for leading soft theorem, you need to do some omega. You multiply by omega and then take omega goes to 0.
So now this derivative will act on, it will act on omega and it will also act on n plus 1. Now say mn in higher dimensions, in mn plus 1, you just directly take the soft limit, there is no contribution from any loop.
Yeah. So what you know is that
But
in
now with the
mn plus
derivative in
1,
mind.
that itself doesn't have log omega.
Yeah. In the real question is, if you compute the same diagram in higher dimensions, it may not have a singular limit. It may be well defined as omega goes to 0, but is it analytic as omega goes to 0?
It will not be. Usually it is not going to be.
His question is that there may be some omega to the n log n, which is not, goes to 0 as omega goes to 0, but if you differentiate it n times, then you see a singularity.
Okay, I don't know actually.
That's an interesting question.
Yeah, I didn't think about it.
Ashok probably knows the answer.
He will know the answer. Maybe he does not, but
I don't know.
that's the question.
Yeah. So the effect of this forces is it doesn't die off as you go to asymptotics. RT goes to infinity. And for example, if we just consider the trajectory of a point particle, it produces a log t kind of term. And so this effect has to be included when we consider asymptotic dynamics. So what happens is roughly, so asymptotically the particles are not free. They still feel this long range interaction, and that is why they radiate. And this radiation has log omega kind of behavior. Okay.
And in high dimensions, the log t would be reduced to
1 over r.
1 over t.
Yeah, so that will just go to 0.
It may be just completely different.
There is no law at all.
Okay, so yeah, so this is a part of the S log coefficient that has this kind of behavior. So this term is actually due to the long range forces that act on the hard particles. And so if we look at this term, then so unlike the usual soft factors, it is sum over like I and j. It is sum over pairs of particles because it represents interactions of two particles. So this this term comes because of the ith particle. Ith particle feels the gravitational field of the jth particle, and the acceleration produces an electromagnetic radiation. That's why it is EI. And this term the jth term doesn't depend on charge because it's the gravitational field. So this term represents that.
So we should think of this as like the Brem star. I mean, because one particle accelerates the other, the radiation caused by that is
Yeah.
universal.
Yeah.
Very interesting.
Yeah. And so now if we look at this term, then it depends on the jth charge also. So this is the long range electromagnetic interaction, and that produces electromagnetic radiation. Okay. So this is how gravity plays a role. Typically, so for leading soft theorem, it's not corrected by gravitational or any other corrections of the theory. But this term has pure gravity effects. Like these are mediated by gravity. That's why it gets corrected. And again, this is a gravity effect. So this okay, yeah, this I have mentioned later. Yeah, and there is one more thing. This first line is due to a Coulombic mode in the gravitational field, and the second line is due to homogeneous mode. So let me just write it down like this. So if you have a hard particle I that feels electromagnetic, so let's first talk about gravity. It feels gravitational field, which is one is a Coulombic mode and one is a homogeneous mode. Okay, and these are these two terms. This is the Coulombic term and this is the homogeneous term.
I don't understand what you mean by homogeneous.
Yeah, so I'll talk about it later. So just naively, this is a source term, and this term, this gravitational like solution, it satisfies the homogeneous equation. So it's that is the naive thing, and we will discuss this later on. And similarly, for electromagnetic interaction, there is a Coulombic term and there is a homogeneous term. And what happens is this turns out to be trivial, so this is not there. The
fact that one charged particle accelerates the other due to Coulomb force does not cause soft radiation.
Yeah. So when I discuss the exact details of these modes, then I will talk about this. Okay, why this is trivial, and yeah. Oh, sorry. And so the homogeneous mode is still there, and that is this term. That is why one term is absent here. Okay.
And sorry, and you said this, but let me just confirm. Even gravitational interaction between the two particles will cause gravitational interaction in your loop will cause both soft photon radiation as well as soft graviton radiation.
Yes, 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 if they are charged, yeah.
And photonic interaction between them will also cause both.
Yeah, but here we are just considering soft photon theorem.
Okay.
That is why this terms so these terms are charged.
Okay.
So similarly, it will be there for gravity also,
Okay.
which will be completely independent of charge.
Okay.
So what was the difference in the structure? So the electromagnetic interactions gives both the soft modes, soft gravitons and soft photons, and graviton, partial gravitons also gives you to cancel also both the soft modes. What is the difference in between?
No, there is no difference. But here I am just considering soft photon theorem.
Yeah. But she was saying here between these two terms, there's some, what I understood, and please correct me if I'm wrong, is that she's saying that this acceleration has two pieces. A path that you see classically and a path that you don't. The path that you see classically is just the Coulomb force of one particle of the other, and that term does not cause soft photon radiation. Whereas the classical gravitational interaction between the two particles does cause soft photon radiation. Okay, but then there's, in addition, some quantum correction on both sides, which exists even for the electromagnetic case.
Yes.
Is that right?
Yes. Yes.
So somehow the Coulomb force, the simplest one, does not cause, and she
Yes. 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 Yeah, and so this term, the homogeneous term, is absent in classical theory. And but all the terms are same order in h. All are h to the power 0, the Planck's constant. So this is a little bit puzzling, and yeah. So let's discuss in details later on. Yeah. Then this part of the log coefficient, it comes from the acceleration of the emitted soft photon. The soft photon that is emitted, that itself undergoes some kind of acceleration. And these terms are produced due to that acceleration. Now, since this is uncharged, it is not affected by the long range electromagnetic acceleration. That's why there are only two terms here. Okay, so for soft particles, there are only gravitational two terms, Coulombic and homogeneous. Okay.
Can you say the last thing you said again, please?
Yeah, sure.
You
So
said the photon itself. Sorry, please say it again.
yeah, so the soft particle itself feels the the long range forces by the other hard particles.
So in this case, it feels only gravitational force.
Yeah, because it's uncharged.
Right. Okay, that's what you said. That's what you said.
Yeah, yeah. That's why there are only two terms here.
And this is what you call the homogeneous mode?
Yeah, so this is the homogeneous mode again, and this is the Coulombic mode.
Oh.
So you see here there is a k dot pj. Here there is a pj dot pi. So this pj is replaced by k.
What is K?
K is the soft photon momentum. So actually here it depends only on the angle. The omega will just cancel. So everything has to depend only on the angular momentum of the photon. So roughly, yeah, Q is the this thing, yeah. So K is equal to omega Q. So this entire thing can be written, maybe I should have written it like this. So this is also QQ, the omega just cancels. So everything on the right hand side, so this should just depend on Q, because that like it has the angular dependence of the momenta of photon, soft photon. Okay. Okay, now
Whole answer is sum from these two factors?
yeah, it's sum over ij.
No. This is this one and the earlier slide you had.
Yeah. So the total, this is the total thing. These two are coming from scalar hard particles. These two are coming from the soft particle. Okay, so let's now we'll try to understand the construction of charge. So once we have these things in mind, then we can just try to understand the effect of long range forces on asymptotic dynamics and see how we can try to understand the log omega mode. So first let's discuss asymptotically free scalars.
Sorry, the reason that the classical processes were order h bar is that the charge of a classical part of one particle
So
has
just
an h bar.
so actually it is h to the power 0.
Ah,
Both are h to the power 0.
h to the power 0. Oh, sorry.
Yeah. So the surprising term is thing is that the piece which is not present in the classical theory, that is also of h to the power 0. Okay. So we will be working with massless scalars minimally coupled to gauge field and gravity. And first let's consider asymptotically free scalars. Okay.
Only contentful, sorry, not all of them are content. Only important statement is that if you have Coulombic force for electromagnetic radiation, then that does not give you soft photons. This seems to be the statement that you made somewhere.
Yes,
This is correct
yes,
statement, right?
yes, yes. Yeah, actually what happens is maybe, okay. So I should say this, if you consider in general, then that interaction depends on the mass. And since here I am considering massless particles, the mass for massless particles only it becomes trivial. If this if the scalars were massive, then that term is there. So Alok considered massive scalars, and there he reproduced the term from the charge also. Okay. So only for massless scalars it becomes trivial. Okay, so now we will study dynamics around Scribe plus. So so we start with the flat space time in retarded coordinates and just take r goes to infinity for fixed u and x hat. Okay. So let's consider the free equation of motion of scalars since we are considering asymptotically free scalars.
Is there any way of computing these diagrams in dimensional regularization? Let's say some 4 plus epsilon maybe.
Yes.
And then one can see how they are going away. Sorry.
Yeah. Yeah. Okay, so so this kind of equation it admits an asymptotic expansion in 1 over r, and so this phi 1 acts as the free data for this equation. All this phi 2 and the higher order terms can be fixed in terms of phi 1.
Why
And
don't we have log somewhere? Wait, you have 4 dimensions.
yes, so for free scalars the leading
Free scalars, so
yeah.
you haven't.
So when we introduce long range interactions, then we will have logs. And so if we want to work with the quantum theory, then the usual creation annihilation operators, those are related to this free data phi 1 just via a Fourier transform. Okay. Now similarly we can expand Maxwell's equations.
So you are in asymptotically flat space time, right?
Yes. And now using the fall off for phi, we can find a fall off for the u1 currents. It is just 1 over r expansion. And yeah, so just let me go back 1 minute. Yeah. So what we will do is we will collect the coefficients of the 1 over r terms. Okay. And then we can see that so in particular we will be interested in FRA. Okay, A is ZZ bar. So our coordinate system is U, R, XA or Z, let's call it ZA. Well, ZA is ZZ bar. So later on we will define the asymptotic charge in terms of FRA. So that's why I'm just looking at FRA. Similarly, it can be done for all other components also. So FRA starts at 1 over r square, and this component has to satisfy this kind of equation. And here again this AA0 that acts as the free data of the photon. Now so we have to give a profile for the free data to fix the U fall off of FRA. Now this is a profile that is consistent with the tree level soft theorems. If you have a 1 over omega term, so like if this is the energy expression, then a 1 over omega term is related to this u to the power 0 term. Similarly, then if you say that your next term is omega to the power 0, then it will tell you that there can be no power fall-offs in U. Okay, this is so this means that there is no power fall-off in U. Is it okay?
Why do you need to Taylor expand right now? Is it necessary?
Yeah, so I am trying to find out the U behavior of the of FRA2. Okay.
Saying the corrections from constant cannot be power law. They could be exponential, e to the power minus, e to the power plus.
Yeah.
Okay.
Yeah, so I'm just trying to take a profile for the free data to fix the U behavior of FRA2. Okay, and with this profile, I see that the leading order term is U. Okay, so here you see this is the U is, so it's always U by R square. Then if you go to the next order,
Leading order in what?
so this is around U goes to plus minus infinity.
U is large, right? I mean.
Yeah, U plus minus
I didn't
infinity.
understand this. I got confused. What is that statement UA0 equals U plus U 1 by U to the infinity?
Yeah, so this means there is no power fall off in U.
There's no power fall off, but you're allowing U and U squared and so on?
Okay, so let me, so this is the A0, okay, and this is, yeah, this is this term. So the del U of this term is related to a del U square of FRA2.
Okay.
So that's why you, so the constant.
Oh, I see.
Yeah.
So the different ways of parameterizing the same thing.
Yeah. Yeah, so this has a order U term, okay. And now what we will see is that we will include long range forces in all this. To this point, we had considered a free scalar.
Sorry, but that was some field strength that's blowing up as you go to spatial.
Yeah.
Is it really blowing up?
Yeah. So.
It's not blowing up because R is taken to infinity first.
Yeah. So it's typically the field strengths have this kind of behavior. So here the power of U. So if you take it to be M, then M can have n minus 1. If this is n, then Maxwell's equations tell you that FRA has typically F mu nu, some components of F mu nu, they can have U this kind of terms.
As you said in the beginning. Why is this component becoming, whatever it is, why is it becoming bigger at infinity? Isn't it strange, or just is there some?
You are saying it's suddenly dominating at infinity? Like
No,
that?
I mean, let's. I mean, is there an interpretation for the fact that this coefficient, whatever it is, as FRA over R squared, the coefficient of 1 by R squared in FRA is blowing up at U equals minus infinity?
No,
Can I think of this like the Coulombic? What is this FRA? I mean, physically, is it like a Coulomb force or is it a radiation field?
So right now we are considering Coulomb. It's a radiation. So in 4 dimensions we can differentiate between sourced and unsourced terms. Since both Coulombic and radiative fall-offs are same.
Okay, just suppose I had a static charge. Would it produce an FRA? I get confused with this R and U.
It's a radiating moment. It's a radiating moment.
Yeah. So let's go back to the earlier slide. Yeah. So you are saying that this.
Suppose that was just in the time dimension. Point particle sitting on the origin. Is that producing FRA or is it producing FUA? It produces one of the two, right? Which one?
If RU, it will produce FRA.
Yeah, so it will not produce FRA because this depends on JA, the spatial velocity.
The other one is
I see, radial. Thank you. FRA. So this thing I should think of as radiation. FRA.
Right. I guess so.
Yeah. So
whatever is happening, why is it happening more at scribe at infinity?
okay.
Or it's not. It's some fake. You're saying the real But radiation should go to 0 at infinity, right? That's at u equals minus infinity. Why am I not seeing that?
Yeah, so radiation need not go to 0 at u goes to
Oh,
minus
this is the soft
infinity.
mode.
Yeah, typically we have this kind of terms are typically present in FRA, which diverge as you take u goes to plus minus infinity.
Okay. Now I don't doubt that it's true. I just wanted to understand what it meant. But please go on.
Yeah. Okay. Okay. So so to this point we have considered free scalars and the corresponding free currents, and that has produced this kind of field. And next we will include long range forces on the scalars, and then try to see what kind of FRA it produces. And so there is an additional log u term here that will be so we will see how that is produced. Okay. So let's consider gravitational coupling first. So the equation of motion for scalar is corrected by this term. This is the most dominant term at large R. There are other 1 over r square corrections which we are ignoring. So this is the dominant correction, and HRR1 is the 1 over r component of HRR. So this is in the sense like codifying the dominant effect of the long range interaction, the 1 over r term. Okay. And so we can just solve this equation, and the solution looks like this. So it like expected, it produces a dressing of the free operators B and D dagger. This is the dressing, log r dressing
HRR1 is the coefficient of 1 by r
of HRR,
of HRR.
the 1 over r, the long range force actually. Yeah, so here I'll make some comments about the electromagnetic intercoupling. So so I have not written down those terms, but similarly there will be a AR1 term here. So let me write it here.
And this HRR1, I'm sorry, but HRR1 is what is, how should I think of that physically?
Yeah, it's a potential.
It's the Coulombic potential,
Yeah.
the Newtonian potential.
The
caused by a
Newtonian
mass.
potential, yeah. The classical mode is exactly the Coulombic potential. And
So this is the motion of the scalar field in the Newtonian potential.
yes,
RR1 is like mass stuff. Zero mode of RR1 is mass. Hello.
zero more.
Bonding.
So actually what happens is, if you consider radiative term, because zero modes you have to construct from the radiative terms, these are Coulombic modes. Okay, and
What is the mass in terms in this gauge? You are working in a gauge for the gravitational field.
yeah,
In this gauge, what will be the expression for mass? Suppose I have a black hole.
hmm.
This RR1 would be integrated version of RR1 would give me the mass.
Yeah, so here I am working with massless scalars.
For the gravitational part, let's say, how does mass look like in this gauge?
Yeah, so here my scalars are also massless, and so for massive scalars, you want to construct the mass from the gravitational data.
Okay, so suppose you take a asymptotically flat black hole, and then you expand around this infinity in this gauge, a particular gauge you have chosen. RR1 will see the mass of the black hole, right?
No, so it will depend, but typically UU will see the mass.
It's not bonding gauge. What is this gauge? It's not bonding gauge.
Hmm?
This is not bonding gauge.
Yeah, this is not bonding gauge.
RR1 is not related to mass. This is very confusing. Why RR1 is not related to mass?
So
It really depends on your gauge, right?
It depends on your gauge. She is working in some gauge.
Yeah.
But in that gauge, if I want to compute the mass of the, suppose you have an asymptotically flat black hole, you take its field and Taylor expands in this gauge, and you want to calculate mass, then would it be true that in each RR1 integrated over sphere in this infinity would
not to 0.
Sure. So that would be another gauge.
Yeah, so it depends on whichever gauge is working.
Yeah, so if you so
Right,
the
it
gauge
is
that I'm
gauge.
working in, so I am just constructing the solution from retarded Green's function right now.
I understand, but in this
And so if you take a massive particle, static massive particle, then if you integrate HRR1, then it will give you a mass. But I am working with massless particles. That's what I'm saying. Okay. Okay. Yeah. So this is the analog of Faddeev-Coolidge dressing for massless particles. Okay. Yeah, and I was talking about the electromagnetic counterpart. So if we just consider the electromagnetic term, that will be something like AR1 del U phi, this kind of term. And so what happens is AR1 becomes trivial. The Coulombic part of AR1 that becomes trivial.
Coulombic part of AR1 becomes trivial because you mean it's 0. It becomes trivial.
Yeah, it's just a constant. It can at max have a constant.
And why is that? It's just a similar kind of thing because it's massless or something?
Yeah, for massive particles it's non-trivial actually. So AR1 is just proportional to the mass. Yeah, probably.
So it sounds
yeah.
similar to what you're saying. HRR1 you said is also for a massless particle was not. What was it for massless particle?
For massless particle, HRR1 is trivial. Sorry, it's non-trivial.
No.
Yeah. But if you consider a static massive particle, then it can tell you its mass.
And this is the reason somehow that the difference between the gauge field and the gravity.
Yeah, actually, physically, I don't understand it any better. Like why I can just calculate the expression for AR1 and say that it's trivial. But if you ask me physically what is happening, then it's not clear to me.
It falls off faster. Your point is falls off faster. Some of
No,
that.
no, no,
Your
no, no.
claim is that it falls off faster.
No.
Can you say? Your
Yeah. So okay. So since I'm working in the what is it called, Lorentz gauge, I can just give my solution. J mu. Okay. This is the x minus x prime square. Okay.
This is the Green's function.
This is the Green's
Okay.
function, and turns out that my AR1 is just trivial. It doesn't depend on the momenta of the particles.
It's like, is this the statement that the Lienhard-Wiechert potential of corresponding to a massless charged particle? If we work that out, I mean not the Lienhard, wherever that out, the potential, the solution, and then you look at the motion of another massless particle. No, then you look at the motion of another massless charged particle in that potential. It just is undeviated at infinity. Well, the same is not true for
Massive. Yeah, for
that's not true
gravity.
for gravity.
Yeah.
That's a surprising situation. Yeah.
It is deviated, but not in the right order as well.
Yeah, so one way is like the massless particles will continue to move in straight lines in absence of gravity.
Exactly. Even though there are two massless particles, they exchange in Coulomb, but they continue to move in straight lines
Straight
at
lines.
infinity or even at finite distances.
At finite distances, it's just it depends on the gauge. In some gauge, you can just think of it like a point-like collision.
How can it depend on the gauge? I mean, it's a physical question, right? one massless particle going this way,
Hmm.
and in the background of that, if I've got another massless particle moving, it'll move on some trajectory.
Yes.
And are you saying that it's a straight line exactly if the impact parameter is non-zero? It's exactly a straight line, or only at
Yeah.
only far away?
So actually, I have some confusion there because we can. So when we study the interaction of shock waves, which are also solution to massless equation of motion, then it is exactly like that. It's straight lines, some deflection, and again straight lines. So it's exactly a point, like.
It's a point, and if there's an impact parameter,
Yeah.
there's still a point.
So again, it's instantaneous. So the next. So let me. Yeah. So.
These circles are made of what? These circles are made of metric fluctuations or?
Yeah, so we can consider both, like massless gauge field also, or massless gravitons, like massless scalars also. What I mean is you can construct shock waves for a mu also or g mu nu also.
So let's construct a shock wave out of a mu nu. Then in this background, if one other charged particle moves, and his question is about how does that.
Yeah, then.
I don't even say what shock waves are. Can I just look at the trajectory of one particle? And just as a classical question, Jackson question, look at, and then produces a potential, and then I look at the motion of another massless particle in that background. This is the clear question, right? It can't depend on gauge or anything like that. It will have some trajectory. It's not just the trajectory at infinity that's physical, the whole trajectory is physical.
Yes.
And we can ask what it is. And are you saying that it's exactly a straight line? Or you're saying something, you said something I could understand.
Yeah. So if you are considering like collision of two shock waves, which you can treat like two massless particles interacting, then asymptotically these particles are exactly free. Okay. Now when I try to study the same question in this by constructing solutions of this form, then I see that asymptotically the particles have some other modes in the potential also. Okay, and so that's why I thought that it's a gauge dependent statement. In one case, when I'm like modeling my massless particle as a shock wave, then asymptotically I have only two shock waves. There is no perturbation around them. Okay, but if now I'm just taking the same source and constructing this kind of solution. Okay, and this solution has other modes also.
Yeah, but you're doing something more complicated than I wanted. Just something very simple. Suppose I just take a particle moving along a null line. It has a certain J mu. I put that J mu into Maxwell's equations, I solve for it in any gauge. Then I look at the motion of another massless particle in that background. Well, I don't understand why we need to talk about shock waves here.
Yeah, so I think that which part of trajectory is radiating, that is a gauge dependent statement.
Which part is radiating depends, but the shape of the trajectory is not gauge dependent.
Okay. Oh. So I was thinking in terms. Oh.
Okay, we can talk about it later.
Yeah. Probably you're talking about charged particles.
Yeah.
Okay, I was thinking in terms of like gravitational shock waves.
Yeah, gravity is trickier.
Okay. Yeah. There it's difficult to say how it's gauge dependent.
Excuse me, am I audible?
Yes.
So I have a question for Sayali. So you only mean that only asymptotically the trajectory is a straight line, right?
Yeah.
So it's not that even in the bulk, if you are looking at the scattering of these two particles, I mean motion of one particle in the field of other, it's going to be a straight line. It's only asymptotically that it's a straight line.
Yeah. Right now I remember. So I was not understanding like what part of trajectory the radiation comes from.
Right.
Is that a gauge independent statement or not?
I mean that should be a gauge independent statement, right? I mean.
So under gauge transformation, some part of trajectories might get mapped to each other, right?
That is right, but that's in the bulk. What you're saying is that in asymptotically, it's going to be straight lines. It's not going to be affected by by the field of, or the presence of the other particle.
Just in electrodynamics, the trajectory of a particle is gauge independent.
Yeah. For it.
Not only asymptotic part also. Say in case of gravity, you create a hopper, other particle is going through it. It gets shifted as it goes past the hopper. So asymptotically, it's moving in another line. There is a non-trivial interaction which will be captured here. So it's not only asymptotic, it's all the trajectory that we need to know, like the massless, two massless particles. It's not just asymptotic, it's more than that.
Yeah, so that's the confusion actually. So
but the equation of motion that you have written, that is true just asymptotically, right?
Yeah.
It may be only asymptotically that will result in this log omega.
Yes, that might be the case. In this example, it is not important.
Okay, yeah. So so the thing is like the physical reason exactly is not clear to me, but the if I just calculate this expression, then it turns out to be trivial and doesn't contribute to the log omega term. Okay. Yeah. So when we consider the dressed scalars, then it now the follow for the current also changes. There is some log r terms here, and so this log, the coefficient will depend on HRR1. Okay. Now we can just put in these sources in the Maxwell's equation, and then try to find the gauge field.
Sorry, what was the last transparency again? What are you computing now?
Yeah. So this is the U1 current.
The U1 current due to this to what, the deviated particle.
Yeah. So you like U1 current with this dressed scalar.
Okay.
Earlier it was this dressing was absent, so this log r term was absent. Okay. Now this JA log gets related to a 1 over U term in free data by Maxwell's equation. So what we have is the free data has a 1 over U term. So to compare without the long range interactions, we had this kind of behavior. So there were no power fall offs in U. And and the other thing is like this, we can just consider the Fourier transform of this term, and it produces a log omega mode. So this is very nice. Like we just included the effect of long range interactions in asymptotic dynamics, and we see that the photon has a new log omega mode. So here also it's clear that the log omega mode is directly related to the long range interactions, and also it also tells us that when we exclude the long range interactions, then this is absent. That's why it was absent at the tree level processes. Okay.
I see. So sorry, just to make sure I understand. Did you see completely asymptotically? So please one transparency back, please. One more.
One more. This.
Yeah. Right. So you computed J, and then you related J to this photon from the IISER. Thank you. So you computed J from knowing the trajectory.
Yes.
From knowing the deviated trajectory.
Yes.
And then you related that to some soft mode of the photon.
Yeah, to some mode of the photon. Yeah, and now one can again find the FRA term, and we see that it has a new log U term, where this is directly related to this 1 over U term. Okay, so this was absent in our earlier analysis.
Yeah, have you yet shown us this homogeneous?
No, not yet. Yeah, it will be at the end. Yeah, so just to now everything, like all the long range, the effect of gravitational long range term, it is in this HRR1, and that HRR1 has two. We'll see that it has two components. One is Coulombic, which we usually discuss, and the other we will show that it has some non-trivial homogeneous term also.
Sorry, in your formula, when you were introducing Ashok's formula, you have these two kinds of terms. One due to the deviation of the hard particle, and one due to the deviation of the soft stuff. This one is the deviation because of the deviation of the hard particle.
Yes.
We haven't yet seen the second.
Yes. Okay, so yeah. So let's at the future we saw that there is a new log u term, and when we do the similar analysis at scri minus, then we see that there is a new log r term, and so
I'm slightly confused about the follow-up. So you assume certain kind of gravitational fields for which you computed the trajectory, which is one higher order interaction. When you plug back that trajectory and calculated the gauge fields, it corrected by log u. Now, presumably, if you put that back, it will affect the gravitational fields in a higher order. Yeah, it's something like that.
yeah, you are saying continuing this process for the next order
But they will be higher orders.
in coupling constants.
In higher orders. Because the assumption about when you assume that your gauge field falls off in a manner to calculate the trajectory of the particles, there if you assume that has a log u term to begin with, that will not get affected. This is the only question. At the end, you found some particular column that if you in the beginning assume that it has a non-zero contribution of
it does not get affected. That one can check. So so Alok and Miguel, they had discussed massive sources, and there also so the similar thing has to be done at time like infinity, but when they calculate the field strengths at null infinity, then they have similar kind of fall off, that there is a log u term and there is a log r term, and they had proposed this kind of conservation law that relates the log u term to the log r term.
Why this is 2 and 0?
Yeah, so here you don't have a log v fall off. If you consider retarded boundary conditions, then a log r term gets related to log u. Yeah, it's a rough way to see expect. In coordinate systems you can get this, but this has to be rigorously proved. But what you can do is take retarded propagators, take the same sources and consider retarded propagators. Then you get a log u term at scri plus, but a log r term in scri minus.
Which is same sentence that change the coordinate system and match.
Yeah, but it is. I mean, naively you cannot claim like that. At least in some cases you need some checks, right? Yeah, so this is the new conservation law, and from here we can construct the charges. So
but here this can be verified explicitly. For example, in proof examples, this is true, this can be checked.
Yeah, that's what I was saying. You can consider point like sources, for example, simplest case, point like currents, and then consider the keep in the log t corrections at asymptotics that you take into account, and then try find the field strength at scri plus and scri minus. Then you will see that there is a log u term at scri plus and a log r term at scri minus.
This is roughly, is it the same statement as the following, that in space like infinity, if you look at on the compactified Minkowski cylinder, if you look at on the cylinder, map the Minkowski space, then there is this, the null geodesics cross each other. It's the same statement as this is continuous, or is it more than that?
So no, actually these are in classical theory these are dynamical statements, because to evolve from one slice to other slice, we need to use the Maxwell's equation.
If you have static charges, they will have FRU.
You mean static charges FRU?
Massive static charges, they will have FRU non-zero, which will have some profile and tri plus.
Oh, you are saying check? Yeah. You can check it like that.
For that, the condition was that just map it on the cylinder, and on the cylinder in space infinity, two null generators cross each other, and you just claim that it is continuous at that point. Here, if you do that construction, it is equivalent to saying the same thing, that it is continuous at that point. This condition.
Yes.
Same thing.
Yeah. Yeah, and so we can construct the charges. So this is at a particular slice, scri plus minus. You typically, so we write it as an integral over entire scri plus minus the scri plus plus term. So this gives us the soft charge, and this is the hard charge here. Okay. So yeah, so this is the soft charge, and we can use Maxwell's equation to simplify this this term and relate it to free data. And to parameterizing this Vz like this, where it is it depends on two z prime and z, so that this z will then denote the angular dependence of the soft momentum, soft photon. Okay. And so then doing the integral, we get this kind of expression. So this choice, when we take a non-zero Vz, then it gets related to the negative helicity insertion. If we had chosen non-zero Vz bar, then it gets related to the positive helicity insertion.
If you don't choose this particular vector field, some other vector field, you can find out a basis of vector fields on the sphere and look at all the other components. And in explicit examples,
yeah. So this the Ward identity is true for all V's.
So can you check that explicitly in QFT by doing a computation that all of them are true? This will probably give you the standard soft theorem.
Yeah. So
if we don't choose this particular, I should get some identity.
Yeah.
Can it be checked through an explicit computation?
So in principle, yes. So that will be like, it will be related to the some non-trivial combination or non-trivial operators acting on the soft theorem only. In general, it might be combination of both the negative helicity, positive helicity soft theorems. Also, some derivatives may be acting on the same or something.
I understand, but this is not a complete basis. It's a very specific choice, right? It's a very specific choice. So, do you know any paper or you yourself have tried to compute?
So here actually what we are doing is, though we are choosing a particular functional form, but still we are introducing an additional freedom in terms of this z. Here the Ward identity holds only for v depending on this z prime. Okay. So in the trade-off between this z prime, the functional dependence, we can vary the functional dependence, but instead of that we are introducing that degree of freedom by making Vz itself depend on another z. Okay. And so this operator is the same operator that picks out the log omega term. Okay, so we have the correct soft charge, and so Ward this is the Ward identity. So on one side we have the soft photon insertion. That
so where did that choice of that z, one slide back.
Yes.
The choice of z, where did that go away in the final answer?
Yeah.
That went into x hat.
Yeah, x hat. So this z bar they parameterize some direction which is given by x hat. Yeah, so this inserts the soft photon, and this hard charge should act on the states and produce the soft factor. Okay. Now we have obtained one contribution to FRZ log that comes from the dressing of this hard particles, the scalars. And so then just solving for this FRZ, it turns out that this is the contribution can be written like this. This is the same operator that we saw in the soft theorem, and it's just this operator acting on HRR1. Okay. So to recall, so this I have just written the same expressions, a soft insertion and the soft factor. And this was the Ward identity. When we can write it in terms of the amplitude, mn plus 1 and some mn here. So the soft theorem has these two factors. Okay, that look like the terms that we have reproduced from the dressing of the hard scalars. Okay. And so and these two terms have then should come from HRR1. Okay. Now to produce the second terms. which should come from the dressing of soft photons. So similarly, we just consider the leading order correction to the free equation of motion.
And so again, sorry, have we seen these homogeneous pieces yet?
No. Okay, so let me tell what I'm going to do. So everything I'm just writing in terms of HRR1, okay, and so similarly I will find the contribution to the soft theorem from dressing of the photon. That will again I will write in terms of it will depend only on HRR1, and at the end I will evaluate HRR1. Okay. So the leading order correction to the equation of motion of the gauge field, it is again governed by HRR1, and we can just find the contribution to the charge. So again this is the free data. It has a 1/u term that comes from this piece, okay, and it contributes to the charge, and we see that this contribution, it depends on the leading soft mode. That's how we get this S0 factor. So the contribution from the photon dressing, it is of this form, HRR1 times S0. Okay.
So, you have to trace. No.
Yeah. So we saw that the long range effect on the scalars that produced S1 hat HRR1 term, and similarly the dressing of photons produced S0 HRR1 term. Okay. Now next we need to evaluate HRR. So this is the soft theorem. This is like this word identity looks like this now, and we need to evaluate HRR1. Okay. So in the
you finished solving for A in the background of this HRR1?
Yes, that is given by this. So this is the correction that is relevant to us, that actually contributes to the charge.
Okay. So this is similar to the solution of the phi in the background of this HRR.
Yes.
But
But the
same question. This solution when feedback to the scalar equation does not give you non-trivial.
no. Yeah. And so one thing is like from here we can see that this is directly related to the leading soft mode. Okay. So this mode is absent for the scalars. That's why the scalars don't get a 1/u correction. Scalars got a log R dressing. The similar log R dressing is present for photon also, but that is not relevant for the charge construction. For the charge, the photon mode that contributes is 1/u, and that comes only from the leading soft mode. Okay. Yeah. So this is the Coulombic mode. You just we can just find the solution by substituting the relevant T mu nu here, and the solution looks like this.
I see. So in terms of your diagram, either you have a photon emitted and then moving in the background of whatever, or you have this internal photon. But the diagrams with both are not important.
Yes. So this is the Coulombic mode, and yeah. So now we can discuss the this is the homogeneous mode discussion. Now a generic homogeneous solution in d dot gauge, it can be written like this. So you have CZZ and
So what do you mean by a homogeneous solution?
Homogeneous solution is box of h mu nu equal to 0. And the d dot so this solution satisfies the d dot gauge condition, del mu h mu nu equal to 0 and box of h mu nu equal to 0. And so here this is the free data, CZZ and CZ bar Z bar, and so you give any profile for free data and this can generate the solution for you. Okay. Now let's look at HRR. So here I am just not writing CZ bar that term.
Wait, so is the general solution radiation or more than that?
Yeah, it will have Coulombic modes also.
Coulombic.
Sorry,
modes
no,
require a charge.
sorry, yeah, I'm sorry.
So It's just pure radiation?
This is pure radiation.
And there's some subtlety with some zero mode sector, or it's just genuine radiation?
I don't understand.
Meaning you have radiation at all non-zero omegas, and then is something, are you going to be particularly interested in what happens at 0 omega, or you'll be interested in non-zero omega?
Okay. So in principle, I just want to calculate HRR1, but it turns out that that HRR1 will be certainly related to how the radiative data behaves around omega goes to 0.
Fine. So,
okay.
So this, we have to be a bit careful. I mean, the standard expansion of radiation, which may have some subtleties near omega equals 0, and those will be important for you.
Yeah.
Okay.
So now I'm just projecting it to HRR, and so I will consider this in r goes to infinity limit with fixed u and x hat. So this simplifies a bit. Now what I want to see is if this HRR has a 1 over r term, okay, and so this CZZ, this is a derivative.
Your calculation with the gauge field, you are calculating the correction of the photon due to interactions with graviton. That part of the computation, in that part of the computation, you might have a soft photon. That part you will consider so far.
Wait, can you repeat? I didn't know.
You are calculating equations of motion of the gauge field when it interacts with the gravitational field. And you had some solutions. In particular, that equation can be specialized to soft photons.
Yeah.
So that, did you consider that?
Yeah.
Did you consider that?
Yeah. So here I displayed the how it happens for generic AZ, but the way it will contribute in the word identity, it's only because there is only a soft photon.
She said that it's only the soft photon emission lines that have to be blessed. Right, the leading soft photon emission lines blessed produce that. So somehow she's already got it. Yeah, the effect comes from the other.
Okay, so here this is the first derivative of the free data.
If you had external particles as hard photons, then you would have considered that.
Yeah, so hard photons will contribute just like the scalars.
You consider them as sources to emit new soft particles.
Yes.
But their long range interactions would also be taken care of.
Yeah, so that they will contribute via gravitational long range interactions.
So that part will care about the same equation but at finite omega. Right?
Yes.
That would be like the scalar.
Yes. They will act just like the scalars. So there the log addressing of photons will become important. Here it was the 1 over u term in photons that is important. Yeah. So so here you have to substitute this u to be this term later on. Now if you can get a 1 over r term here only if you have log u kind of behavior in CZZ. Since this is a derivative, so a derivative would produce a 1 over u, and then you have to substitute u equal to r comma something. So an 1 over r term in HRR is related to a log u term in the free data. Okay. Now what happens usually we consider in classic like usual theories we have this kind of behavior. This is a long range effect, and leading order term is u to the power 0. That's why we know that for homogeneous solution usually radial gauge is considered, where this HRR1 is set to 0. Okay. Then from there what we would expect is that HRR1 doesn't have any information about the homogeneous solution. But now what we will see is that if one is careful, then a log u term in CAB, there is a non-trivial log u term in CAB. Okay.
I'm completely losing the physics here. This homogeneous term was, if I thought of it as a radiation field, I could imagine just some radiation mode going on. What is the principle that's determining what this homogeneous field is?
Yeah, so here the only control like I have on the or I am using for this homogeneous solution is the right soft behavior.
Right soft behavior. What you're forced to turn on this homogeneous mode for some reason?
Yeah.
What is forcing you to turn
Yeah,
on?
the soft behavior. So when I have the so my leading soft theorem for graviton, that is also forcing me to pick out a log u term here that we will see.
Wait, yes, so just to understand the structure, you say that we know some leading soft behavior.
Yeah, yeah.
You put that back into the equations
Yeah, yeah.
at infinity or everywhere?
So I'm doing all this asymptotically.
Asymptotic. You put that back in the equations at infinity and you use that as a source and it will create something else.
Yes, yes, yes.
Gravitons are charged under themselves. So if you solve that equation, won't you fix this automatically? The gravitons carry energy,
Right.
so they interact among themselves.
Right.
If we solve that equation and look at late time behavior,
Yeah. But at late times I assume the only thing that matters is a constraint equation. So somehow like solving a constraint equation at late times forces turning on something.
yeah, I was imagining
Okay.
that this will fix this.
Yeah, I think that's what you said, right or not?
Sorry, can you?
So you have some soft graviton being emitted by a leading soft graviton because of some leading soft graviton. Now, once you have that, you're forced to turn on something else.
Yes, yes.
We're trying to understand what forces you. So
Okay.
at infinity, gravitons become free, apart presumably from some constraints. So it's the constraint equations that are forcing you to turn on something.
No.
No?
Okay,
Okay.
so let's just see it. Yeah. So I just considered the Fourier CU, the Fourier transform of CU. So I have just eliminated the indices here, CZ.
I'm getting a little lost. The C, for instance, I can't remember. What it is.
Yeah. So this is this CZZ or CZY
One of
ZY.
the terms in the metric.
Yeah, it's the free data of the graviton.
Fine.
Quantum mechanically, it's related to the creation annihilation operators.
Fine.
Okay. So I'm just considering the Fourier transform of the free data. Okay. Now from the soft theorem, I know that it has a around omega goes to 0. It has 1 over omega term.
Meaning and omega, some soft gravitons are emitted from the leading soft theorem.
Yeah.
That's the statement.
Yes.
Okay.
Yeah.
Yes. Go on. Yes, please.
Now I can just try to study this expression around small omega,
Okay.
and then we can then it will introduce some log u terms. Okay, so let's
just
I
Fourier
can do it.
transforming.
Yeah, they are just Fourier transform.
Okay.
And then what will happen is if this field is continuous at omega goes to 0, then this will just cancel. Yeah, so let me write it.
Plus and minus.
Yeah, it is from the omega positive side and minus side.
Okay, this is roughly like the large
Yeah.
gauge transformation on the gravitons.
Yeah, so but here I have not done anything like this is just simple. I'm just doing this d omega by omega Fourier d omega by omega, and I'm saying that if it is discontinuous around 0,
Yes.
then it will produce a log u term.
Okay.
Okay. Now now what we will do is we will just study the quantum version of this operator. Like this will be an operator.
And you know that coefficient has to be 0? Is that coefficient 0 or non-zero or what?
So usually we always this is always taken to be 0, because we the radiative data is always taken to start at u to the power 0. In other words, we always assume that this is continuous at around omega goes to 0. Okay.
So
Okay.
the coefficient of C plus is the same as the coefficient of C minus. And what
Yes.
is plus minus again, please?
Yeah. So plus is from the positive side, and minus is from the negative side.
Ah.
Okay. So this here I'm just I mean this is just simple statement
Ah.
that if it is discontinuous at omega goes to 0, then this term is non-zero.
Discontinuity is the coefficient of 1 by omega.
Yeah.
Okay.
And yeah. So now I will just substitute the quantum counterparts of this. Then what happens is the positive frequencies involve the annihilation operator, and the negative frequencies involve the creation operator. So I just write it in those terms, and I have just written as I multiplied by omega and just taken omega goes to 0. That is a trivial trivial thing. Okay, so quantum mechanically this is the coefficient of my log u term. Okay, now what I can do is I can just study the insertion of these operators in S matrix, and what it tells me is that it has a non-trivial action. Okay, so so this is really a non-trivial operator in your quantum theory. Okay, and this is completely fixed in terms of the leading soft insertion. Okay, and so earlier we had discussed that if you had a log u term in the free data, that produced an HRR1 term, right? Okay, and that this is how it contributes to the soft theorem, the log omega soft theorem. So just to maybe I can repeat.
Right.
Yeah.
Right. So wait, just if you don't mind, I try to summarize the logic as I understand.
Yes.
You said that naive analysis tells you that this coefficient of 1 by omega from plus and minus for positive and negative omega is 0. That is the same.
Yeah.
It's equal.
Yeah.
But if you compare with what you get from an S matrix calculation, one loop, let's say S matrix calculation, that coefficient can be interpreted as something in that S matrix, and you find that it's not 0.
Yes.
Therefore, you just put that coefficient, that C plus minus C minus, to be equal to what you see from the this calculation.
Yeah. So, but that's not what. Yeah, one could in principle justify the presence of log u from there.
But
right?
that's not your.
Yeah. So.
Yeah.
So this insertion in the S matrix, it is fixed by leading soft graviton theorem. Okay, so the coefficient of log u, it is fixed by the leading soft graviton theorem.
Okay.
And that coefficient reproduces the log omega soft theorem correctly.
Okay.
Okay, so in principle you could have just fixed this like these are consistent together.
Okay.
It's not that there is a free data in my theory and I'm just fixing it from the log omega soft theorem. That's not what we are doing. It has to be consistent with both leading.
Can you not derive leading soft graviton theorem, not the log omega part, the leading part, the 1 by omega part? Can you not derive it consistently just by looking at interaction of gravitons among themselves?
Yeah, 1 by omega is uncorrected by those interactions.
1 by omega is uncorrected, but the interactions will suggest that there is a log u behavior.
Yeah. This is
In case of the scalar field, naive analysis was some free field expansion.
Yeah, actually this is what we are doing here, no? So this 1 over omega piece, that is getting related to this log u term.
So this should say that once you have 1 by omega, that should
Yeah.
imply that there is a log
Yeah,
log u
exactly,
term, log
exactly.
omega term.
No.
It will imply that you have a log u term.
Yeah, it will tell you it is related to a log u term, and how it produces a log omega, that is via long range interactions.
But wait, could one see this completely classically or not?
Yeah, so
I don't understand why. It sounds complicated to invoke some quantum process.
yeah, so
If you solve the following equations of motion of a graviton in presence of gravitational field of another graviton, if you solve this equation, it might correct the radiative expansion of the radiative field, just like for the scalars it did. Would that be sufficient to get both?
no, there it doesn't correct. This correction only comes from this omega around omega goes to 0 region.
For a scalar, when it was interacting with gravitons, their interactions corrected the free radiative data for the scalar, free radiative field expansion for the scalar. This is correct, right?
No, it doesn't change the u behavior of scalar.
No, we say it changes the trajectory of the scalar. Like you showed us a scalar trajectory.
Yeah.
It's a complicated function. You're saying that similarly the graviton will get changed.
Yeah.
And he was asking whether that captures the physics of what you're saying.
Yeah. I was imagining that.
perhaps you're saying the answer is no, but I had a similar question.
Yeah.
The answer is no.
The answer is no. Yeah.
Okay, please go on. This sounds very interesting.
Yes. Okay. Yeah. So there is HRR1 has a homogeneous piece.
Yeah, I still haven't understood with this homogeneous piece. I've heard some words, but is the physics of it, is it determined classically or not?
Yeah. So classically, so far what people have always restricted themselves to free data of this kind. That's why they are setting the coefficient of log u to 0, and in that means that they are assuming that it's continuous at omega goes to 0. Okay, that's why they didn't see this, because they have set it forcibly to 0.
Is the coefficient of this log u term determined by classical analysis, or you need to
That is not clear to me, because so that in principle I would have thought that this should be determined classically also. Like one should consistently be able to allow the log u term in classical theory also. But so recently Ashok Sen, Bishwajit and Arnab, they wrote a paper where they did all the calculations classically, and they could not reproduce this term in the classical theory. Yeah, so what I understand is quantum mechanically you can fix the coefficient of the log u term, because I can just I know how the operators act.
So if you have a lot of short particles, does that term, is it subdominant compared to the first one? I imagine that instead of having one soft particle, I have a lot of short particles, then that is something like classical process. Classical process. If I have, then I should be able to determine everything from classical analysis. So is this subdominant?
In large and
if you have a very massive particle, let's say.
Yeah, so let me try to remember. In their original paper, they have given some scenarios where the quantum term is subdominant compared to the classical
So
one.
the scenario is this one, right? That you have one, let's say, very massive particle, it is emanating as a lot of soft gravitons, and then you want to do the analysis of soft gravitons in this background. So the classical part should be recoverable from, in this limit it should be recoverable. So if you say this term is not recoverable, is it subdominant?
Yeah, they showed that it is subdominant. Yeah.
Okay, so it's not a classical effect, but can you give some intuition for what causes it? Like your first bit of intuition was very clear, right? That you've got some hard particle and some other hard particle is moving in the background of that guy. That causes a deviation in its trajectory, so it causes it to radiate. That was one thing. And another thing is you've got a hard particle, you've got some soft radiation moving in the background of that guy. That causes it to deviate or to radiate or whatever. That's another thing. These were very clear. Now, is there some intuitive picture for this homogeneous thing?
Yeah. So for this term,
even if it involves something virtual or something, but some words so that you can understand.
So one thing about this term is that it is sensitive to all the interacting particles. Like here for the Coulombic mode, it was pairwise,
Yes.
and here it's sensitive to the all interacting particles.
Okay. Somehow much more complicated.
Yes. And so let me try to think about the original calculation of Feynman diagrams.
Yeah, that would be great. If you could see where in the Feynman diagram it comes from.
Yes. Can I look at that paper and tell you? Yeah. Yeah. So here itself you see this is yeah. So here a particle at x hat, this will feel the effect of all the particles. That's why. So here, just 1 second. I'll go back to the soft theorem. So here we have pairwise interactions for the Coulombic modes, but here we have those are absent. So one particle is sensitive to the effect of all the particles here.
And can I see that in the formula, please? What, which is one with many? Where was that? That is Q is one of the, is what, please? Q is?
Yeah, so Q is the particle that is feeling the effect of the gravitational field. So that Q and the J are the J's
All
the other particles.
It is also like clear. Q is the soft particle. It is interacting with all other hard particles in some sense, one by one.
Yeah. So what happens is for the Coulombic mode, a outgoing particle will be sensitive to the presence of only the outgoing particles.
So for the Coulombic mode, it was say it was always pairwise for Coulombic mode then.
Yeah, it's always pairwise. That is why an outgoing particle is sensitive only to the outgoing particles. It is not feeling an acceleration due to the incoming particles. But here, if you see, a particle at x hat, it will feel the effect of incoming particles also, because it's an homogeneous mode.
incoming particles only or also?
Both.
Oh, okay.
Since it's an homogeneous mode, it's related to both the incoming and out. The interaction between the incoming outgoing particles that produces this mode.
So if I have a soft particle in the initial in incoming, then that will care for the first part. It will care about only interaction with incoming particles. This is the.
Yes. Okay, yeah. So once we substitute this HRR1, then it reproduces the Sahoo Sen soft photon theorem. And the similar story is true for AR1 also. For AR1, what happens is Coulombic mode becomes trivial, but the quantum mode, like this mode is still there, this kind of mode, homogeneous mode. Okay, so just to summarize, we started with a conservation law.
And did Sahoo and Sen have some words for this new? They presumably interpreted the other parts.
Yeah.
But they didn't have any
interpretation for this part.
They did not.
Yeah. Yeah. So they so we can construct the charges, loop level charges for massless scalar QED coupled to gravity, and the corresponding mode identity is equivalent to the soft photon theorem. And so just an outlook. So at loop level now we have a log omega soft photon theorem, and this has been a direct. We saw that in the free data we have a 1/u correction. So that produces a correction to the known memory effects. So this has been discussed by Laddha and Sen. So the other corner of the of Strominger's triangle, they have given a prediction for a tail memory effect, which is the correction to the usual memory effect. And the third side is that we have some asymptotic charges corresponding to this soft theorem, but the underlying symmetry is not clear. So this was the construction of charges is just the first step, and then later then one has to understand if one can make sense of this symmetry as some finite gauge transformations or so on. Okay, so yeah, so I would like to thank Nabamita, Miguel and Alok for many discussions during this work, and thank you all for your attention.
So Bhopal questions?
Oh yeah.
Okay. Mumbai.